Alright guys, so this is the beginning of the end. I'm just kidding, it's just the beginning of calculus. So a preview of calculus is just, we're going to be talking a lot about slope in the beginning, a lot, because of the secant line problem. Okay, so what has happened is, let me bring up, there we go. Let's make an actual line. Okay, and what has happened is that there has been a problem that just works with this. Okay, let's say we do a line like this that represents some model of function or something. Okay, now what has happened in the past is usually if you wanted to find the rate of change at a certain point, you could only do it over an average. So in other words, if I picked a point here and here, I could find the slope of that. Okay, and that's called the secant line problem. Now, does it help with right? Let me pick a different color. Let's pick blue. Okay, does it help with right here? No, it doesn't, because that's a huge average over that time. However, if I pick a point closer, now I'm starting to get closer and closer to it. And so what's happening is my secant line is, if I do this enough, it'll actually turn into what is called a tangent line, which is going to be pretty hard for us to find, but you can actually find it using what is called the difference quotient, which we'll learn later. But as you can see, what's going to happen is that this slope of secant line approaches slope at point, let's call that Q. Yeah, and let's call this Q. Okay, point Q. So the slope of the secant line actually approaches the slope at the point Q, and so that's where the secant line, the secant line becomes the tangent line problem and everything. And that actually leads into something called differentiation. Differentiation. Okay, and this is where it actually comes into play. It's just working on that and just working with it. Here, let me get rid of this one right here. Let's make that a different color. Let's make that blue. Nice blue. And so what happens is we'll be able to, if we get really close with 2 points near Q, we'll actually get and approach the actual slope of the tangent line. So that's very interesting. So we're going to be talking about approaching that, and that's going to be called a limit. So that's why we're going to be discovering limits and stuff. Okay, now the area problem is also another type of issue, and I want to talk about that as well. But the area problem is actually a very interesting idea. Okay, so let's start with let's start out with this. Okay, and let's get okay, something looks like this. Now the area problem actually has this all set up. Okay. Alright, so if I were to find the area under curve, I could do a couple things. Alright, I could do the area on the edge of with some consistently width type of rectangles that look like this, and go to the very edge. Okay, just pretend that this is actually going down to the bottom. Pardon my crude drawing. Okay, now as you can see, I'm missing a lot of area, like this stuff in here. Okay, so I'm actually missing some area. But if I continue this left hand, this is called a left hand approach. Okay, I'm going to overlap sooner or later with the rest. So as you can see, the drawing should be going like this back here, but now I'm getting some back. I'm getting back some actual area. It's not the best. It is an approximation, but it is kind of nice. Let me bring it right there. Okay. And as you can see, let me draw it so you guys can see it. Something that looks like that. So as you can see, all that area I lost over here And right here, I'm gaining back over here. So it does make up for itself. Now you can also do a right-hand approach, a left-hand approach, which is what we just did, or you could do a midpoint. In other words, you go to the midpoint of it. But it doesn't matter because it's just going to be an approximation. Now, what mathematicians, and especially Leibniz and Newton, have discovered is like they've sat there and they've gone, okay, what if I did like an infinite amount of these boxes? Okay, now there's no possible way we could actually measure that out. Okay, but what if we did an infinite amount of these boxes? Okay, and these boxes, you guys, these boxes, here, it's hard enough drawing them. These boxes have to be infinitely thin, and as you can see, I'm cutting off less area of it, and I'm actually going to get really close. And so the closer I approach infinity, the closer I am of filling up this entire curve with these boxes and stuff. And as you can see, my horrible drawing has really kind of outdrawn itself and just worked with it and got some interesting ideas. But the interesting idea is that if I get a number of these infinite boxes, and what we would call this right here, this width of the box, and this is really mind-blowing, we would call this delta x. It's just the change in x as we go, and obviously the change in y would change as we go, and so what we would have to do is do some calculations with it. But it's really interesting that we could find the area of this by finding the area of an infinite amount of rectangles. Now if you try to do that actually by hand, it would take you forever, which doesn't exist. But it is helpful in understanding, like, okay, now I've got this, now I think I've got a really good idea of what is going on, and we can just work with it, you know. Okay, so rates of change and limits, you are just approaching numbers, you're getting really close, and you're going to be approaching infinity but not getting there. So a lot of interesting stuff popping up. Guys, this is a preview of calculus, and we're definitely going to be talking about finding limits in this whole unit, okay? All right, I will talk to you guys later.